Okay, this one summarize for us what we have covered, except in explain fusion and fission. Okay, let's do some partial question so that we are aware what type of question you are going to encounter. When uranium-235 nuclei are fissioned by slow-moving neutron, two possible reaction. Reaction 1, reaction 2. For reaction 2, identify the particle C and state the number X of such particle produced in the reaction. Okay. Complete the nuclear reaction for reaction 2. What is X and C? Write a nuclear equation. No? Right. Total number of nucleons. Left hand side 235 plus 1. This is 2 times 116 plus your X. So X is 4. C you have to identify. So conservation of charge. Right. 92 plus 0. 2 times 46 plus Z. Z for C. Z equals to 0. So the emitter particle is neutral. This is a neutron. No? C is a neutron. And 4 neutrons are emitted. Can?
Yep.
Binding energy per nucleon for a number of nuclides as given a table. State what is meant by binding energy per nucleon of a nucleus. Can remember? Can? Binding energy per nucleon is the total energy needed to completely separate all the nucleons in the nucleus divided by the number of nucleons in the nucleus. Okay?
Alright.
Okay, try the next part. This is an old question, but show that the energy release is in reaction 1 is 210 mega electron volt. Yep. Can get the answer. That's your reaction 1.
Okay.
Energy release. Right? Since you are given binding energy, you start with the product first. Binding energy of product minus binding energy of reactants. Right? That's 139 nucleon times your 8.339 and 95 nucleons times 8.74 minus is 95, 8.74 This one doesn't have binding energy. Can we should get 211 mega electron volt.
Okay.
The energy released in reaction 2 is 163. Suggest the reason which one of the two reactions is more likely to occur. Yep.
Tomo.
Which reaction? One or two?
Reaction as in.
More binding
Oh,
energy.
okay, okay.
The attractive force is stronger.
Yeah.
Binding one is reaction one is more likely to occur as more energy is released in the reaction. Thus, the daughter's nuclei are more stable. Okay, it is unstable. A lot of energy want to release. So if form the daughter, then you release the energy. Okay, suppose a stationary uranium decays spontaneously in thorium-234 nuclei emitting an alpha particle. Write down the nuclear equation. Yep, write down the nuclear equation. Right? Thorium-234 has more, as it is more stable. Energy is released when uranium decays to thorium. Okay. If you won't complete it, if you want, you can try it out yourself. Let's try something. Okay, try this one. The following reaction given you deuterium combined with deuterium to give a helium-3. Determine the mass defect. Yep. Mass defect, mass of reactant minus mass of product. Right? Mass of reactant, deuterium. Mass select, there are two of them. These two. Mass of product, mass of product. There's neutron, one neutron. Can get
Times two. Yeah, can.
binding energy per nucleon, E equals mc square. Can
6.3.
6.66 and 10 to the power 14 joule. Can
Cup.
is the reaction endothermic or exothermic?
Exo.
Exothermic, good. Let me see any more question you want to try. Don't want to try too many. Uh, Okay lah, the rest you try yourself lah. You go to radioactivity. Okay, can see the slide? Yep,
Yeah, I
yep,
can see the slide.
can see the slide. Radioactive decay, exponential nature of decay, define activity, decay constant, define half-life, the relationship between half-life and decay constant. Okay? Don't worry about all that. You can use your textbook. That is your syllabus. Okay? And exponential decay is given, right, in terms of x instead of n or a. Then decay constant is given you. Know where to find the formula. Okay. Types of isotopes. Natural isotopes. Stable isotopes. Naturally unstable and emits radiation. We call these radioisotopes. Artificial isotopes are produced by bombardment of stable nuclei with high energy charged particles, example neutron and proton, alpha particle. The radioisotopes are isotopes of an element that are radioactive. Background radiation. Natural isotopes provide most of the background radiation. This one is for United States. So radon is 37%, radon and thorium gas in houses. Gamma rays from rocks and soil in the earth. 17% from radioactive element in the body, mainly C15. Cosmic ray from space. Medical, mainly from X-rays. 1.5 fallout, nuclear waste, and industry. So these four accounted for 87%. Natural one is about 87%. Different book will give different, slightly different, but don't have to worry lah. Then know that the main one will be radon and thorium, and then gamma ray lah. These two are more. Radon is more dangerous because it is radioactive and it can migrate to long distance. Right? The half-life is about 3 days. So it will decay and then the decay product will stick to dust. So especially if you got a cellar or a small closet in your house, you have to clean the dust up. If not, radon is a gas. It can sneak into the house anywhere hidden. And then as it decay, the product, right, it's a series decay. Product will be attached to the dust and it's radioactive. Right? So that's the danger. Okay. What is radioactivity? Memorize it. There's a symbol that if there is any radioactive material around or there's radioactive experiment around, then usually we will have a sign there or radioactive material being used. That's a sign. Right? That's a simple. Radioactivity is the result of decay or disintegration of stable nucleus by the emission of particle or particles and sometimes accompanied by emission of gamma rays to form a more stable nucleus. Okay, the original nucleus is called parent, unstable. It decay to daughter. Right? These two are different elements. Example of plutonium, and then this alpha particle. Radioactive decay of nucleus is essentially independent of the environment of the nuclei. That means it can be an atom, or it can be a compound, or it can be a cold environment or high pressure environment. So it's independent. It doesn't affect the radioactivity. Parent and daughter are usually different elements. Right? His daughter, parent are different elements. Textbook will use decay or disintegration, or sometimes transmutation. It's a spontaneous and random process. Spontaneous decay is one that is unaffected by environmental changes such as temperature, pressure. Right? Just happen. It doesn't affect by temperature or pressure of the environment. Random process cannot predict which particular nucleus will decay next. How do we know? It's one of constant probability of decay per unit time of nucleus. How do we know? From observation? Fluctuation in count rate provide evidence for random nature of radioactive decay. Right? Random sometimes you detect more, sometimes you detect less because it is given out in different direction. Right? That's the decay curve. This is the how is the random nature of the emission shown on the curve? Yep. Any idea? How is the random nature of the emission shown on the curve? How do you know on the curve? Yes, it's random nature. Yeah, muted. Yeah, muted. Yep. How do
Is it the fluctuation? Like there's a bit of spike.
the curve is not smooth?
Yeah, it's not smooth.
Random nature of the emission is shown by the curve being not smooth. Sometimes it emits more, sometimes it emits less in a particular direction. Okay, sometimes random is sometimes it emit one direction more, sometimes in a direction less, right? So it emits in all direction. So CPM is count per minute. How is spontaneous nature of emission shown by the curve? Yep.
Spontaneous. You can start at any counts per minute.
No, the curve is the same, whether you put it in high temperature or low temperature environment, or whether you put in a cold temperature or hot temperature, the curve is the same, right? Identical curve. Okay,
Yeah.
spontaneous mentioned in the syllabus. Law of radioactive decay, rate of disintegration of a new given isotope, radioisotope at any time is directly proportional to the number of atoms n present at the time t. Okay, so we can write a differential equation. dn dt equals to minus lambda n. Lambda is called the decay constant or probability of decay, right? It's a Greek alphabet, lambda. Okay, decay constant, we can rewrite that. Lambda, right? Change it to delta m over n. Right? There's probability of decay or fractional, right? Fraction decay, probability of decay or fraction of decay, right? Decay during this time interval lah, delta t lah. You say per unit time. Decay constant is probability of decay per unit time. Right? Lambda is the probability of decay per unit time. Right? Delta m is small change in number of particles divided by the original number of particles. The number of particles present at that time lah. Fraction of total number of atoms present per unit time, right? Fraction, or probability of decay per unit time. Provided the unit of time is small. Unit per second or becquerel or count per second. Different radioactive, different isotope decay at different rate, and the rate is constant. Right? This one is in the syllabus. Right? This is a solution to the differential equation. Number of radioactive isotopes at any time is given by that equation. Right? The syllabus is given as that, where n is n naught is the number of atoms of certain radioactive isotope present at initially or at time equals to 0, right? Where you start the counting. N is the number of decay at time t, number undecayed at time t. Right? It's an exponential decay. Okay, fraction remaining will be just take n naught down there. Fraction remaining. We won't bother about derivation. This is just for your info. Right? You're not required to know the derivation. Decay constant and T half of a substance are specific to the isotope of an element undergoing radioactive decay. Right? Different radioactive elements have different decay constant or half-life. For example, bismuth 210 can undergo a decay to Tl206. Right? Half-life is 5 days. Whereas bismuth 215 undergoes beta decay to polonium 215. Half-life is about 7.6 minutes. Okay, activity or intensity is defined as the rate of disintegration of number of substance or the number of nuclei per the decay per unit time. Right? As in mathematical form, rate of disintegration of the substance, and we have there's the decay law. So from the decay law, we know that A can be written as that law. Right? Is the count per second or disintegration per second of becquerel. So it's given as n lambda. Okay. Right? You're required to recall and use. 1 becquerel is equal to the activity of 1 disintegration per second or counts per second. Curie is defined as the quantity of any radioactive material which undergoes 3.7 times 10 to the power 10 disintegration per second. It will be given you if it's required you to convert to Curie. Half-life. Half-life is the time taken for radioactive isotope to disintegrate to half their initial number of nuclei. This formula is found in the formula sheet. You just need to know how to use it. It's given as this form. radioactive decay of bismuth, half-life is 5 days. Right? If we start with 100 atom or 100 gram, then after 5 days, 5 days it will be 50 left. After another 5 days, right? Half of 50 is 25. After another 5 days, which is 15 days, half of 25 is 12.5, and carry on. Don't bother about deriving it. Okay, alternative formula. Right? Start with at time 0 and not. So after one half-life, and not or 2 left. After another half-life, half of this one. So after n half-life is n naught over 2 to the power n, no? Right? N 2, 2. Fraction of parent material that remains after the radioactive decay can be calculated using the equation. Okay, this alternative equation. Fraction remaining, we like using exponential, can use this equation. You find this is easier. Right? There's a fraction remaining, where n is the number of half-life elapsed. Time lapse is t, number of half-life lapse times t half. T half is the half-life. Or we can use, this is a fraction remaining, either formula. Amount remaining, fraction decay, fraction remaining, fraction decay. So we can use either formula, this formula or that formula. Okay. Any comment or anything not clear?
All right.
You need to know how to draw the graph lah. If you start with n naught, and then half-life is t half, then after one half-life, 0.5 will be left. Another half-life, 0.25. Another half-life, half of that one will be left. Okay, so you need to know how to sketch the parent decay curve. And then the daughter will be just same. You will start from 0. Daughter will start from 0. And then you will be here. There will be a point here. And then this one will be 2 square from bottom, from the axis. Is 2 square from the top. Same thing. This 1 square from the axis, x-axis, or time axis. This 1 square from there. Okay. So you should be able to draw that, sketch that. Right? This one is poor. I shouldn't touch. I should be parallel like here. Parallel. Okay. Make sure you know how to draw that. Number of daughter increases. Number of parent decreases. At half-life, number of parent equals number of daughter. Curve runs parallel to the time axis after 5 half-life, showing that the number of radioisotope does not decrease to 0, but only in finite time. Okay, there's a formula. We take natural logarithm. Right? The one will be written in this form. Compare the equation of straight line. Right? This is your time for 10 more minutes. There's your ln n, log to base e lah. Plotting ln n versus time give a straight line graph. Huh? Give a straight line graph with negative gradient. Gradient equals to minus lambda. Right? From this equation, gradient equals minus half lambda. Right? Y-intercept. This one is ln L naught. Ln N naught, sorry. Now we can use a log linear graph. This is not common anymore lah. But it does come out in AS lah. But this type of graph paper very hard to find now these days. Right? I can roughly show you for your info. Right? Instead of calculating it, taking log, we can use a graph paper that's called log linear graph to find the half-life. Right? 100 becquerel activity, half-life 10 days. Right? That is the table. Start with 100. 10 days later, 50 left. And now 10 days later, 25 left. So you can plot the graph there. Right? This is natural logarithm. This has to be 10. Cannot change to, it can be 1, it can be 10, it can be 100, it can be 1,000, but it cannot be 20. Right? Same like this one. Right? This is 1, 10, 100. And these are the points obtained from this table. And then it show you a straight line. No? Have you seen this? There? In your AS work, this is your AS graph, log graph.
Yes.
Okay, half-life of radioisotopes are different for different elements, right? From very small to very large in years, from second. Half-life varies from very small in second to very large, millions of years. Okay, calculate activity of a piece of radioactive material is 4.3 times 10 to the 5 becquerel at time t equals 0. Number of undecayed atoms in material at time t to 0 is 7.9 times 10 to the power 15. Calculate the decay constant. What is your answer? 10. That's your A. That's your N. Use A equals to N lambda. Right? This is your A. That's your N. Then lambda, calculate lambda. Then half-life can get the formula from the formula sheet. Right? 0.693. And then take this line, put it around, substitute in. Okay, anything not clear?
Okay.
Activity after 4 half-life. Calculate. You can get the answer. 2.69 times 10 to the power 4 becquerel. Right? Can either use the exponential formula or use this formula. Either one. Can get the answer.
A not. Yeah.
Then number of undecayed atoms after 4 half-life. Same, just use the formula, that's all. Right? This formula, A equals to N lambda. Calculate N. A we have already calculated there. N is what we want. Lambda. That's your lambda.
Teacher.
Yeah.
Elapse means total.
Say again.
Elapse means total.
Let me pass the time pass.
Oh.
5 later. Okay, for half-life later. Or time activity after for half-life. No? Can, anything not clear?
Good.
Right? Alternative, you can do exponential lah. or use the definition lah. Okay? Half of it left after one half-life. After another half-life, half of it left. Half of it left after another half-life. Okay? And then there's your four half-life. Activity of source. Right? This one is not mentioned in syllabus. There's your source there. There's your detector. The detector has a cross-sectional area A. So activity of source is emitted in all directions. So we are detecting only a small section by the detector. Right? C. Detector C. Right? Source of radiation is assumed to give out radiation evenly in all directions. Detector has a cross-sectional area S to detect radiation and usually place a distance R from the source. The radiation detected is counts per second. Right? That's the count, the activity detected by the detector lah. Activity of source emits into a sphere of surface area 4 pi r square. Right? Activity is proportional to area. So using that we can calculate our activity of source. Okay. The activity detected by detector, area of detector, right? The ratio must be the same. Okay.
Okay.
Measuring half-life, we just use the equation, no? A equals to n lambda, right? The equation. No? And then we have completed it. Anytime it will go off. No? Remaining 2 seconds. Right? Small
I
lambda,
see you, teacher.
large lambda.
Eh?
Any comment or anything
It's
to
okay.
ask? Yeah, okay,
Love.
or combination, right? This is a combined curve of these three radioactive elements. This part is decay of iron, 59. This part is decay of cobalt. Application is for your info only. Okay, you can read yourself. Right? It won't ask you. But related to physics, calculation, yes. Right? Cosmic ray collide with nitrogen. Neutron capture produce your carbon-14. Take by plant. Animals eat the plant. The body become radioactive. Okay, so we have summarized for you. Okay, see you next Tuesday.
See you, teacher.
Bye bye.
Bye.
Right, there's a summary of what we have learned.
Yeah, I think we should have class every Tuesday and Thursday.
I see how. I see how.
Okay, because haven't finished medical and astrology.
Okay, I see how. I see how.
Alright, thanks, teacher. Bye.
Okay, bye bye.